All right, friends, we're back. This is chapter 10, and we're going to be estimating means with confidence this time. So we just got done with a couple of chapters where we were estimating proportions, either with confidence intervals and eventually hypothesis testing. And now we're kind of going to rinse and repeat and do it all with means. Um, I am very excited, not just because it is, getting to the end of the course, and not because I want to be done with the course, although you might feel differently, but because this is that moment where all that familiarity comes into play and things start clicking. Hopefully, you've reached a little bit of that already. All right, so section 10.1 is going to be estimating a population mean. We're going to work on confidence intervals here. So, we have a few learning targets we're going to take care of. And in class, I would kind of do this as a discovery activity. And before I show you any notes, I might ask the students to say, what do you think would be the formula to find a confidence interval for a true population mean? So they might think about what we did in the last couple chapters with confidence interval formula for proportions. And really, on the formula sheet, the generic formula where it says statistic plus or minus critical value times the standard deviation of the statistic, that's the only formula they give you for confidence interval. It's very, very general because we have to kind of tweak it a little bit depending on what we're working with. So today we're going to talk about estimating the mean of the population. So if you think about what statistic goes along with mean, we know that's going to be X bar. So you're going to have sample data, you're going to have a sample mean, X bar, and then normally we'd call this Z star value this critical value. What we're going to learn in a moment is it's not Z star today. And that's because we'd love to use sigma divided by square root of n for the standard deviation, but guys, if we don't know the population mean, I really doubt we know the population standard deviation. So we have to do some tweaks to this formula as well. So in class, we're going to do this activity where we kind of show you this confidence level creation applet. And we know what confidence levels mean. If we're doing a 99% confidence level, that means 99% of our confidence interval should hit, quote unquote. But when we do this for the means instead of the proportions, it's not coming out right. Like this example here is only showing it like 92%. Um, that's not right because we had a 99% confidence level. So what's going on here? And the issue is a lot more missed than we wanted because the standard deviation of the sample, S sub x, is much smaller than sigma. So we weren't hitting our target, basically, was the issue, at least not at the capture rate that we were hoping for. So what we're going to need to do is we need a larger critical value. The critical value that we get from Z star isn't quite going to work. And oh man, I should have Googled this, but there's a lot of history that goes along with what we're about to use. We're going to use what's called the T distribution. I don't want to put it on record as to what the history of this is because I'm sure I'm going to get it wrong. But before I teach this in class, I promise I'll Google it and make sure I get the right story. All right, so what we're going to do instead of finding Z star, we're going to find something called T star. And it is the critical value based off of a T distribution. And I think this graphic really helps. So the purple distribution, that's our standard normal distribution. Well, we're going to have what's called degrees of freedom, where we basically are going to try um, we kind of want to replicate the normal distribution, but like we can see, like this red one here, that's with what's called 2 degrees of freedom, and it's not matching up with the purple one at all. So you'll notice the spread of it is not quite what we're looking for. So they modify the critical values so that way you have a more appropriate margin of error, and that's where these T star critical values are coming from. Now, to find all of this, the first vocab term here that I threw out with no introduction whatsoever was degrees of freedom. So a degree of freedom is going to ask you to basically take the sample size and subtract 1. That's the idea. Now, there's a couple of ways we can find this T star value. Table B, which if you remember, I gave you guys a little hint that we could actually find Z star on table B as well if we go to the infinity level. But besides that, the rest of table B is going to help us find T star values. So the first question is a 95% confidence interval with a simple random sample of size 12. So if we are going to find a T star value from table B, what you do is you flip to table B, and first thing you do is you get the correct row. So a degree of freedom is going to be your sample size minus 1 if that's something that you can find on the table. Now, what you'll notice on the table is, I don't have one in front of me, but it goes down to like, I don't know what number, 25 or something. I forget. And then it starts skipping. Obviously, if you have like 1,000, that table would be gigantic if they listed every single integer. So they start skipping a little bit. So I'll show you what to do in that case. But using this table is going to work for a lot of our problems when we have smaller sample sizes. So degree of freedom would be 11. That came from 12 minus 1. And then if we want the 95% confidence interval, we think about, okay, how much, percentage is in the tail of that distribution. So the inside 95%, the tails split that extra 5%. So splitting 5% is 2.5%. So you follow degree of freedom 11 over to where it hits the 2.5% column, and then boom, there's your T star value that we're going to be using. My friends in class, this is the infinity row, and there's our friend 1.96 that we used a lot when we were doing um, uh, you know, one sample and two sample for estimating the population proportion. Anywho, T star for that problem was, I already forgot, 2.201. So for part B, same question. Well, no, it's not. A 90% confidence interval this time with a random sample of 48 observations. Now, you'll notice the table starts skipping. Okay, apparently when it gets to 30, maybe it starts skipping by tens because they don't want to keep counting by integers. Well, 47 would be my degrees of freedom technically. You'll notice 47 is not on the table. So if you're using the table, if you're going old school, you're just going to have to go to the one that you can go to, the next one that's available, which in our case would be degrees of freedom of 40. Remember, these are all approximations. So as long as you're using a valid method, an approximation is just going to have to be good enough. So remember, it's a 90% confidence level. So the tails are going to split that extra 10%. So your probability of your tail is 5%. And that's where they're getting the 1.684 for the T star value. So today it's a T star because it's coming from the T distribution. You'll notice that title is at the top of table B. So if you're ever thinking, what on earth am I doing? Just look at the title. Now, you know me, I love technology. There are other ways that you could find those T star values. And instead of inverse norm, because we're not inverting the normal distribution, we're inverting the T distribution, you're going to go to the same place, but you're going to pull up inverse T. And I think on my calculators, the newer ones, it does prompt you. So it's going to ask you for that left tail area. So the split tail. So in that first problem, it was 2.5%. And then the next thing is going to ask you, if you're doing an older calculator, you got to type in degrees of freedom, which would be 11. Now, on the example after that, where we had to estimate with the table, it didn't have 47 as a degree of freedom row. When you're using technology, you actually can go ahead and type in the 47 for degrees of freedom. And look how the answers compare. So off the table, was that there? Yeah, that was it. 1.684 compared to 1.678. So again, estimation, these are approximations, they're close, that's all that counts. And the fact that if it's a free response question, um, you're going to need to make sure you justify, how you're getting this number. Maybe. It depends on the question, I suppose. All right. Oh, spoiler alert. There's the answers. Okay. So we have same questions. They would like you to use table B on these problems, though, so that way we all get the same answer. So a 96% confidence interval based on a random sample of 22 observations. So first, you got to get the right degrees of freedom. So 22 minus 1 is 21. There's your degrees of freedom row. Then it says, if possible, check with technology. Yeah, we will. So what we did is, I don't have the table in front of me. Oh, so this is dumb. So 96%, the tails are going to split that extra 4%. So you're looking for a tail of 2%, and then a degree of freedom row of 21. So if you follow that over, T star's coming out to 2.189. Now, if we do that same problem using technology, using an inverse T distribution, 2% degrees of freedom of 21, and what do you know, we get 2.189. Remember that lower tail T star value, it's going to show up negative because it's a critical value off of the left side of your curve. So think of it like an absolute value problem. Negative 2.189 is equidistant from the mean for the positive 2.189, so it's an absolute value question. All right, the next question was degrees of freedom of 70. So 99% confidence level here, guys, you got to split the 1%. So you're looking for 0.005 in the table up at the top in the 70th row. Oh, turns out that table doesn't have a 70th row. You got to back it up to 60. Bummer. All right. So anyways, you get a 2.660 if you use the table. Now, if you use the technology piece and you invert the t-distribution, the lower tail of 0.005 with degrees of freedom of 70, you get 2.648. So again, if we compare the two, they are not exactly the same. And that's because this was using a table where we had to approximate because we didn't have the right row and the right percent. We didn't have the right row for degrees of freedom. And technology, of course, is going to be more accurate because technology is working off of a calculation, which is an infinite table, right? All right. So that's how to use the table and or technology to find your critical value. So now let's talk about the conditions. And I think you're going to have a warm, fuzzy feeling here because it's the same conditions that we've worked with for what it feels like forever. The random condition. It's crucial because if you don't randomly sample, you can't take your conclusions and then extend them out to a larger population. So if you can't do that, why are you even doing this? When sampling without replacement, which is typically how we sample, 10% condition is what allows us to use the standard deviation or eventually the standard error formula. So that way it's close enough, basically. So 10% condition, got to check it unless there's something weird happening in the problem where it's not necessary. And then remember in proportions, we did the large counts condition, but in means, we look for, back in the day, it was a large enough sample with the central limit theorem. And then today they're going to call it the normal / large sample condition, which it parallels with the large counts condition. So I like calling it that because it helps my brain remember what I'm looking for. I'm looking for a justification that we are going to be approximately normal. But in this case, it's going to be appropriate to use the t-distribution instead of the normal distribution. Again, I got to Google the history of the t-distribution. If memory serves correct, oh man, it's something with, gosh, I can't remember his name. Oh no. Anyways, a great former statistician who worked with I want to say he worked for Guinness. Anyways, he was working in a factory and he was doing like small samples and he was doing statistics with his samples, but and again, don't hate me up, people out there, if you work for Guinness, but I believe the issue was Guinness was really secretive about their formulas and recipes, and they didn't want like anybody putting out any data from anywhere. And this was a long time ago, but they didn't want people putting out any information about how their beer was made, basically. And this statistician published a paper on his findings of doing a bunch of small samples and created essentially the t-distribution. But he didn't call it that. What happened is he published his paper, I think, and then he called it like a student. Like that's how he signed it because he didn't want to get fired. Um, so unfortunately, he had really sloppy handwriting, which speaks to me because I too have sloppy handwriting, and no one could read his handwriting. So when he wrote a student, like all they could decipher was the letter T. So the stats community started calling it the T distribution. I believe that's the story, but I'm sure someone out there on the internet knows the real story, and that probably isn't close to it. All right. Anywho, so here's our conditions all on one screen. The randomization condition allows you to extend your findings to a larger population. 10%, if you're sampling without replacement, we need to satisfy the 10% condition. And then the normal / large sample conditions. Oh, I never even went over this, duh. If the population is already normal, then cool, you're good. But if not, you need to have a sample size that is large enough. Remember, we referred to the central limit theorem earlier in this unit or last unit, I guess. And the population distribution, if the shape is unknown, but your sample size is less than 30, so if you don't meet the large sample size cutoff, then what they suggest, because if you can't say it's normal, then you're kind of sunk and you can't go any further. They're going to want you to graph a sample data set to assess the normality of it. So if you were able to graph like a histogram or stem and leaf plot or box plot, and you could say, oh my gosh, it's fairly symmetrical. There's no outliers. There's no strong skewness. There can be a little skewness, but nothing crazy. In that case, you can still go ahead and use the T procedures. So, like I said, if you can't use the T procedures from this point, then we're kind of sunk and we can't move on and make estimations. All right, so here's an example of some data. We have average GPA of students at your school, and you randomly select 50 students for your sample. Here's a histogram. Well, that's great, but I don't really need the histogram because 50 is bigger than 30, so the sample size is large enough. That means I have met the normal large sample condition. So this next one, how much force does it take to pull wood apart? Here's a stem plot of a random sample of 20 selected pieces. Now, 20 is not bigger than 30, so we wouldn't be able to satisfy the condition unless I could look at the distribution and say, oh yeah, it's symmetrical. It looks normal. And turns out this one's not. It's very strongly skewed to the left, and possibly with some low outliers. So I'm not going to be able to use the T procedures from here. So we're going to have to do some other statistics, I guess. Possibly get a bigger sample size, eh? All right, so now we have some new data about the mean SAT math score at a large high school. And they have a box plot and they sampled 20 students. So right away, 20 obviously is not bigger than 30, so I don't meet that large sample condition. However, when I look at that data, and I know some might argue it's right skewed, but I would say it's slightly right skewed. It's not a significant skew. So you're going to say, yes, there is a little skew, and no, the sample's not big enough. But when I look at the data, it's pretty decent looking. So we're going to go ahead and be able to use the T procedures. And there's no outliers. That was the other issue. Remember box plots outliers, they put little stars usually. All right. If the question on the AP exam asks you to construct and interpret a confidence interval, all the conditions should be met. You still have to state the conditions and show evidence that they are met. So I know sometimes in our homework problems, they sneak a little like message at the end that say all conditions have been met. Well, that's not going to happen on the free response questions. So you actually have to go through and show that they've been met, and that's kind of annoying. And today that includes the fact that, oh, if I don't meet the large sample condition, then I have to give some sort of a graph of the sample distribution if it's too small, and then show that it was, kind of normal looking, or at least doesn't have outliers and significant skew. That seems like a time-consuming process, doesn't it? That is why they only give you 6 free response questions, guys, because they can take a long time. All right. Constructing a confidence interval. Deja vu, guys. State, plan, do, conclude. It's the same. So that's the part of stats that I really love is they teach you how to take a procedure and apply it to various methods. And when we change the type of data we have, like here, instead of um, uh, oh my gosh, categorical data, we have quantitative data. So that's the issue. We're changing from proportions to means, and the process is the same. So that's a little heartwarming. Of course, the formula is a little different. We just learned that yes, our statistic is going to be X bar, but for our critical value, because of how our data is collected, or what type of data we have, we can't use Z star. We're going to use T star from the T distribution. So that's good news, I guess. And you will find some information, just like with the proportions, where you can Frankenstein this formula together on the formula sheet. So, you're going to have that generic confidence interval formula, and then if you turn the page, it's going to start talking about, one sample T intervals and population means and all that good stuff. The degrees of freedom idea, you have to remember what that means, of course. All right. Oh, looks like we're going to have to put some thoughts together now. In Chapter 8, we learned about the 73% of Americans who claim they have read a book in the last year, which I found appalling. I thought it would be higher than that, but the kids all assured me that that number is probably too high in their opinion. So, wah wah. So they had a random sample of 1,520 American adults. Same study also reported that the average number of books read by the members of that sample, and they included people who read zero, the sample average, their sample mean was 12 books with a standard deviation of that sample of 18 books. So step 1, they want us to construct and then eventually interpret a 95% confidence interval for the mean number of books read by all Americans in the previous 12 months. So obviously we don't have that data. So we're going to try to create this confidence interval to estimate where we think the data of the true mean. Remember, doing means today. The true mean of all Americans, number of books that all Americans have read. All right. Enough babbling, Abruzzo, get going. Now, the act of construct and interpret, guys, that's a four-step process, right? We have to state. So we start with 95% confidence interval for mu, which is the true mean number of books read by all American adults in the previous 12 months. Now, I know in proportions we made a big deal about like putting the right language here. The mean is a little easier to describe because it's just going to be, a quantitative number. A mean is quantitative. Categorical, when we did proportions, it was like the P was the true proportion of people who would say that blah, blah, blah. We don't have that issue with language here in means. It's a little easier. Remember how means play nice? They play nice in language too. All right, so then we're going to plan it. And notice they just have, this is the only parameter they have to define. So that's the state level. So now we're on the plan step. We're doing a one sample T interval, right? This is a T interval, not Z, for mu. So check your three conditions. The random condition is applied. Check, check, 10%. Yep, that's less than 10% of all the American adults. And then the sample size was 1,520, which is definitely greater than 30. And we learned the hard way on a Frappy last chapter that you literally have to say it is greater than 30, and that's why that condition is satisfied. Oy. So now we're going to do the work. And I am going to show you how to have your calculator help you check your answers, but we still encourage you guys to do the work this way, even if you're fudging it and you're like kind of doing the work. I want to see the setup at the very least, and they're going to want to see the work and not necessarily just that you can crank things in the calculator. Now, the reason we are really trying to have you do it the long way is because they will often ask questions in the multiple choice section where you have to kind of work yourself out of the formula. So having a calculator might not be very time efficient. Using the calculator method for finding the interval isn't going to be helpful, or at least not helpful in a short term. Like you'd have to plug and chug numbers until you got the answer to work, and that's not time efficient at all. So the formula is crucial. Practicing with it is crucial. When it's game time, if you can take a shortcut, do it. But for now, practice the long way. So what we have here we have our statistic X bar, and then we have our sample standard deviation. And then somehow you need to find T star. So whether it's with technology or the table B. Now in table B, because your degrees of freedom, they don't go up to 1,519, you'd have to round down to the next line that works, which would be 1,000. But when you compare that to technology, they're claiming it's the same number. I have a feeling that's a typo. I think this is a different number. Oh well, we'll figure that out in class. So you're always safe to go with the table B answer because that's how us old dogs do it. All right, X bar, 12, plus and minus, the T star value you just found, and then your standard deviation. Uh-oh, what happened here? Oh, I feel like something got weird. Let me go back to the problem real quick. There's a typo. Gosh, be golly, I gotta fix these. Right here. This is supposed to be 18, isn't it? I am not redoing this video, guys. You're just gonna have to live with my mistake. Okay, so yes, that standard deviation is supposed to be an 18. I'm gonna write a note to myself. I gotta fix all this. This guy right here is supposed to be an 18. What is that? Is that even from this problem? Guys, that's not even from this problem. Ugh, I'm not recording this video again. I'm sorry. That's your X bar. That's your standard deviation. I don't even know what MV is. I bet we're going to find out. It's probably from another problem. All right, anywho, this work is great. And then it creates this confidence interval. So there you be. And I'll show you in a minute on the calculator how to confirm that that's your confidence interval. So now we're going to interpret it. So just like we did before, we are 95% confident that the interval from 11.09 books to 12.91 books, make sure you got labels on means, captures the true mean number of books read by all American adults in the previous 12 months. Okay? So make sure that parameter explanation is at the end, not the sample. Man, this is like riddled with typos. That makes me so sad. I need to fix that. I even previewed this. My pea brain didn't catch that. All right, part B. Yada, yada, yada. they reported that people read an average of 14 books. So they want to know, how does your interval kind of correlate with that claim? So remember, our interval went from 11 to not quite 13. Um, does your interval provide convincing evidence that the mean is different than the 14 books? And like, yeah. So in our interval, 14 isn't even in the plausible range of data values. So our interval gives pretty decent evidence that, and you could go as far as to say it's less than 14, but it's definitely, we're not even including 14. So we do have convincing evidence that the mean number of books read by all Americans is not 14. We'll learn more about directional claims when we get to the hypothesis testing for these. All right. Sorry for all those typos. Next problem. Let's hope for no typos. A manufacturing of high-resolution video terminals must control the tension on the mesh of fine wires that lies between the surface of the viewing screen. That's fascinating, but that sounds scary. Too much tension will tear the mesh, and here's the MV thing, guys. I see what happened. They have some cut and pasting happening where, yeah, I gotta fix that. The tension is measured by an electrical device with output readings of millivolts. I should have known that was millivolts. Come on, girl. Some variation is inherent in the production process. Here's the tension readings for a random sample of 20 screens. So 20, that's not bigger than 30. Okay, we're going to think about this. We're going to construct and then interpret a 90% confidence interval for the mean tension of all screens that were produced on this day. Now, that was important because if you think about the manufacturing setting, the population that they're going to want to be making inferences about is simply everything that was produced that were like these. So, in this case, in manufacturing, it's really important that you kind of narrow down what your population is, especially if you have multiple people or shifts or like manufacturing lines, because how you're randomly sampling is going to affect what your outcome is. Sometimes one machine is broken in the manufacturing process. Okay, I digress. Well, I just really like manufacturing. I think it's cool. All right, so we're going to construct a 90% confidence interval. So stating that 90% confidence interval for the true mean tension of all video terminals produced on this day. So now we're going to plan it. We got a one sample t interval from you. Random, check. 10%, check. Wah wah. Normal large sample does not hit the mark. So instead, we're going to show a dot plot. They went with dot plot. You could have done another distribution, but I like dot plot. And I'm looking and I'm not seeing any like crazy outliers. I mean, I know it doesn't look like a normal distribution, but it's like, it's not terrible. It's not obviously skewed in any way. No strong skew at least. So we're going to say good enough. It's normal enough. So that allows us to use the T procedures. So now we're going to do the work. Here we go. That's the right X bar and S sub X. So we got our sample mean, our sample standard deviation. Remember, our sample size was 20. So with degrees of freedom of 19, you can use table B and find a T star value of 1.729. If you did inverse T, you would get probably something very close to that, if not that exactly. So setting up your confidence interval work, X bar plus and minus T star. And then over here we have the standard deviation divided by the square root of n. So a lot of kids get confused whether they should put degrees of freedom down here. No, the answer is you don't. It's just the formula is n. The degrees of freedom is what's helping you find the T star value. So our confidence interval comes out to this, so about 292 up to 320. Keep those numbers in mind. I bet there's a follow-up question. So we're going to conclude with we are 90% confident that the interval from yada to yada with labels captures the true mean tension in the entire batch of video terminals produced that day. So relating it back to the true mean of the population that they were pulling from. Oh, I lied. There's no follow-up question. It is not enough to just make a graph of the data on your calculator when you're assessing that normality. So they made a dot plot last time. So a lot of kids are like very happy calculator typers, which is great, but then you do need to go transfer it to your paper. You don't have to do it more than once. Just pick your favorite graph and go with it. So think about what would be an appropriate way to display that data. I know you guys have done a gazillion dot plots and they seem babyish, but they're kind of easy to make, right? Like they're pretty decent. Histograms work. You just have to think about what would be easiest for you to construct at that point. box of whisker plots. Of course, if you do it on your calculator, it's not that hard to transfer it to your paper, but you do need to remember to label like the axes. Okay, so now they're going to talk to you about how to have your calculator help you with this. So two things we need to know from a calculator. First, actually, they're just going to jump into the confidence intervals. Sorry, lied about that. Ooh, that is blurry. So if you have a calculator, you're going to go back to the stat test menu, like where we were when we did the z intervals. But this time, because we're t distribution, you're going to choose t interval. Okay, so one sample t interval is what you're picking. And it's going to ask you, do you have data or statistics? Now, if you have data, you can technically enter data into list one and have it calculate from the data. Most of the time, we're going to have statistics. So that's where they give you the X bar and the standard deviation of the sample and N and the confidence level. So you crank those babies into the paste menu. If for some reason you do have data, you tell it where it's located. Either way, you're going to end up with a beautiful confidence interval once you hit calculate. Man, that's nice. So let's try that. All right, we got biologists studying the healing of skin wounds, measured the rate at which new cells closed a cut made in the skin of an anesthetized newt. Oh, that's so sad. Little newt. All right, this is why I could never be a biologist. I don't do the minute they said healing skin wounds, I got a little queasy. And then when I realized it was a newt, I don't know. I don't think I want to do that. Okay, here are data from a random sample of 18 newts. Oh, measured in micrometers to the millionth of a meter. Okay, cool. Per hour. Wow, how do you even measure that? Goodness. Okay, so here's your data. Right off the top of my head, I'm thinking 18, not bigger than 30. We're going to have to do some drawing. And they're going to want us to do the whole shebang, so the four-step process. So first, pause the video. Maybe try this one on your own. I do caution you that you're going to want to draw the distribution. All right, answers coming. Look alive. So first, we're going to state what we're doing. We got a 95% confidence interval from you, which is the true mean healing rate. Now, they didn't give a lot of context there, and I think that's okay. They didn't say, like, in micrometers of per hour for a newt. That would have been really specific. Okay, plan. They are doing a one sample T interval from you. Okay, make sure you got the right language. Randomization was check because they randomly chose them, I guess. 10%. The sample size is less than 10% of populations for all newts. I guess so. Not if you keep cutting into their skin, people. Normal and large sample was not met, however, for the large sample part of that, so they had to draw some sort of a distribution. They went with a histogram. And we're noticing here, I don't see any like crazy skew, and I don't see any obvious outliers. So we're going to say that this condition has been met because of the way the distribution looks. All right, time to do. So we have X bar and standard deviation. So what they have now is they had to find T star value for 95%. And remember the sample size was 18, so their degrees of freedom was 17. So whether you're going to table B or using your inverse T, you're going to get a T star value of approximately 2.110. And plug and sugar into the formula. Make sure this is divided by the square root of 18, because that's your N. And then, because I'm a paranoid person, I would also do my one sample T interval on my calculator with the statistics because actually, you know what? I probably would do it with the data because you probably entered this data into your calculator to create this, I bet. Anywho, I would do the one sample T interval and double check that my interval's coming out appropriately, which it is because I said so. All right, so now we're going to conclude the fourth step. We are 95% confident that the interval from yada to yada micrometers per hour captures the true mean healing rate for all newts who are unlucky enough to be working in your microbiology lab where you're slicing their skin. That's so disgusting. I hate it. Okay, one more idea. I think we're towards the end here. More about margin of error. Don't you feel like we talk about margin of error constantly? But think about it. It's so important. Like, if you want to change your margin of error, like you have to know how to do that. That's a very real life problem. Maybe you're not happy with that margin of error and you want to tighten it up. So the good news is what you're about to see is the same. Margin of error will decrease if you increase the sample size. assuming that the confidence level and standard deviation remain the same. So if you're looking to decrease your margin of error, then pump up that sample size. Margin of error is proportional to 1 over n. Remember, the formula is like square root of 1 over n, you know. So quadrupling the sample size will cut the margin of error in half. I think they meant to put a root sign over this. Another typo to fix. Gosh, I should have previewed harder. All right, the margin of error will be larger if you increase the confidence level, which makes sense because if I have to capture the mean, the true mean, I gotta be that much more sure, so I have to increase my margin of error, make a bigger interval. And then the margin of error does not account for any sort of biases when you do your data collection process. It only worries about sampling variability. So if you have crappy data collection, that's on you, boo. You're gonna have to fix oh, that was it? Okay, you're gonna have to fix the way you did things if you got bias. We know that. All right, so there's one more section in chapter 10. And then we're gonna roll into chapter 11. And then chapter 12 is the end. And they're all kind of short, so we're almost there, guys. Good work. I appreciate everything y'all do in stats. It's a good time. Oops.